In this lesson, we're going to be talking about projectile motion. And basically, in doing so, we're going to be talking about the kinematics as it applies to a two-dimensional problem. Of course, earlier in the previous lesson, we went through the derivation of kinematics equations using XVA diagram, and we were able to do that in one dimension using a calculus-based approach. So I encourage you to watch that video, and that's followed by an example. So we already assumed that we're familiar with the equations of kinematics. Um, and so this is going to be the continuation of that. So imagine we have a soccer ball that is kicked with an initial velocity of v1 with an angle of theta with respect to the horizontal axis. We're going to go ahead and analyze this problem in terms of what happens throughout the motion, derive the applied equations, or not really derive. We're not going to derive anything new in this video, but rather we're going to adjust some of the equations we derived in the previous video. In fact, very similar to the free fall example that we did at the end of the video. So what happens is that the ball is kicked at this angle theta with some velocity v1, and the ball basically goes through a trajectory, and we are interested usually in these 3 points. What happens at the initial condition at v1, we're going to call that point 1. So we're going to basically label the time points that we're going to be considering as we look at the different aspects of this problem. There is a maximum height where the ball will reach, or any projectile will reach, that's going through a projectile motion. And then, at velocity v3, which we can calculate to be the same, later on in the example, we're going to calculate to be the same velocity. This also makes sense. Of course, if we can ignore air resistance and such, then, we can basically recover the same velocity. So this is based on conservation of energy, the principle of conservation of energy. So the other aspect of this is what happens at the very top. So the motion is basically decomposed into what happens along the x-axis and what happens along the y-axis. So we're going to be using the kinematics equations as it relates to these two uh, directions, because we need to decompose the motion into its x component and y component. That's how we can analyze it. So we break it down. Along the y direction, we're under the influence of gravity. So here I'm showing that vector gravity, which is a vector. I'm just showing the magnitude here. I can put a vector sign and make it a vector. This is pointing down, and we are choosing based on this legend here. So we do have to put our legends in physics diagrams in terms of the convention we like to use. There is no default. So here I'm showing that, yes, kind of like the default I'm using to the right to be positive and up to be positive here. And we are saying that this is a constant acceleration motion, and as such, we can go ahead and use the equations of constant acceleration we derived in the previous lesson. So we get equation number one, which is Vy squared equals to V1y, that's the initial velocity, the y component of the initial velocity, which, by the way, here in green, we're showing that V1y equals to V1 sine theta, and similarly V1x equals to V1 cosine theta. So that's going to be, equation one is going to be Vy squared equals to V1y squared minus 2gy. Again, to understand why we're getting this, you got to watch the previous video, previous lesson. The second equation is going to be the elevation. So we are choosing 0 here to be our reference point, to be our origin. So above that would be positive, and to the right of that would be positive along the x-axis. And to the north of that would be positive along the y-axis. So here we have y equals to negative 1/2, negative because the direction of the vector is in the negative direction, negative 1/2 gt squared plus v1y t. Again, v1y is v1 sine theta. So we're usually given that in a problem. We're usually given the v1, the initial velocity, and the angle of the projectile. And the third equation is basically the definition of average acceleration. And this is a constant acceleration, so the average is the same, it's constant, is Vy equals to negative gt plus V1y. So these three equations are going to aid us to track the projectile along the y-axis. So we can talk about its elevation, its altitude. Along the x-axis, on the other hand, if we ignore, remember, one of the assumptions we're making here is ignoring air resistance and air drag. And if we do so, then we experience a constant acceleration motion, constant velocity motion rather. So it's going to be a constant velocity motion along the x-axis. The acceleration along the x-axis is zero, right? Ignoring air resistance. And air resistance can be neglected in such a problem. So then we are going to just deal with simpler equations where the acceleration is zero. So again, from the kinematics equation, we get that v1x equals to v1 cosine theta. So that's this guy right here. That's equation number one along the x-axis, or if you want to call it equation number four, along for the whole idea for the 2D motion. And then x equals to v1x times t, where t is the time in the air, t0 is when we kick the ball essentially, and v1x is v1 cosine theta. So these are the main ingredients and equations we're going to be using to solve any projectile motion problem. So we're going to go ahead and take a look at an example next. All right, now given these equations of kinematics equations for projectile motion, let's look at an example of projectile motion. And in doing so, we're going to look at some of these main time points, time point 1, 2, and 3 that we have along this trajectory. And we're going to ask the following questions. So here's the example right here. It says given v1, v1 being the initial velocity, and theta being the angle of the projectile with respect to the positive x-axis. So these are given. So the expressions we're going to derive and we're going to be solving for, the unknowns we're going to be solving for, we're going to have to express them in terms of these two given quantities, v1 and theta. All right, so I'm going to change the color of my pen right here to maybe, let's say color. We're going to go ahead with yellow here for the solutions. All right. So one question, first part, is asking for what is H max? This is the maximum elevation that the projectile will reach. In order for us to solve for H max, so we're going to do this one step at a time. And then question two is asking us for what is V2. So the number one and number two are very related. We're going to go ahead and solve for number one, which is H max equals question mark. In order for us to understand what H max is, we have to ask ourselves the following question. What do we know about the velocity vector at point 2? So I've drawn it here. I'm going to draw it again just to emphasize. Here's the velocity vector, and here's point 2. And the question is, what is that velocity vector? Well, for one, we know that velocity vector has no y component. In other words, v2y equals 0. You might ask why. Why am I saying that? Well, because this is the maximum height by definition. So at this height, while the y component of the velocity initially was up, it kept decreasing because you had gravity working against the object, weighing it down, and that velocity, that vector, velocity vector goes to 0. So v2y equals 0. Now we know along the y-axis we're dealing with a constant acceleration motion, and if you want to solve for y max, guess which one of these 5 equations I'm going to be using? This guy right here. Why? Because I know, in this case, that Vy at that point is going to be 0. I do know the initial velocity. That's something I know. I can actually solve for that Hmax. So we have V2 y squared equals to V1, that's the initial velocity y component, minus 2g h max. And I can solve this for h max. Noting here that in fact, so we're going to go ahead and change color one more time, just to make it very clear that these are the steps we need to take, that this term here is going to go to 0, because the velocity at point 2 equals to 0. So h max is going to equal to, solving for it, v1y squared over 2g. Well, we know that v1y, let's not forget that v1y, it's right here, is v1 sine theta. v1y is v1 sine theta. We got that from the vector decomposition we did on v1, decomposing it, in fact, into its x and y components. So this is going to be y, v1 sine theta, rather. And we're going to go ahead and square that, divided by 2g. Now, to see if this equation that we found makes any sense as far as h max, which is a height, which is a dimension of length, so it should yield meters. And the way we do this, the way we're going to go ahead and verify the dimension here, is by plugging in dimensions for, in a square bracket, for velocity, and then don't forget that that's getting squared for the square sign. Sine does not have any dimension, sine theta, and then 2 on the denominator has no dimension, but g is meters per second squared. That's acceleration. So as you notice here, we're going to go ahead and cancel the meters squared, and we're going to cancel one of the meters, and we left with meters. So h max, and of course I can go ahead and plug in numbers here if I want to, but h max is going to be v1 sine theta squared over 2g. And who knows, maybe we can use that in the next part or something, but definitely we solve for it. Now moving on to part 2, I'm going to change the color back to yellow here. So part 2 says, what is V2? Now, let's think about that for a second. So we're asking, what is V2? Where is V2 again? What V2? We're talking about this top point at H max, where the projectile reaches H max. Well, V2, we've already decided and determined that its y component of the velocity is 0. So that's that. Well, what about the x component of the velocity? In other words, what is v2x? And what do we know about it? Well, we do know that vx, which is equal to v1x, that's equation 4, at all points along the motion along the x-axis, you're dealing with a constant velocity motion. The velocity along the x-axis does not change. It's v1x equals to v1 cosine theta. So we already have that. It's v1 cosine theta. Again, the final solutions need to be in terms of the given, which is v1 and theta. So that's v2. Now v2, of course, has a direction. The direction is in the I hat direction, in the positive direction, x direction. But what about the magnitude? Well, the magnitude of v2 equals to the square root of the magnitude of v2x squared plus v2y squared. But as discussed earlier, v2y is 0. So v2 equals to v2x, just the x component. So that's that. Now let's move on to part 3. Question number 3 is asking us, what is that final velocity right before the impact? What is that final velocity from a kinematics perspective? All right, that's a fair question, and we're thinking it should be the same as v1, but let's discover it. Let's actually understand what's going on here. Now we know that at v3, now let's see what v3 is. v3 is this vector right here, right before the impact, and this is point 3, and we're asking what is the velocity here. So as you can see, the velocity here has x component going to the right, throughout the motion is the same quantity and the same vector, and it's got a y component that's pointing down in the negative j hat direction. This is going to be the components, and this is what we can talk about. Now, we know that v3x, by definition, along the x-axis, the projectile motion undergoes a constant velocity motion. So v3x is v1 cosine theta. That one is already done and dealt with. I boxed it. It's not a final answer, but I just boxed it to remind us. But we can ask ourselves, what is v3y? What is that? What's the y component? Now let's think about it here. Let's think about it here. We can use different equations for this, and a few different equations can work out really nicely. But number one, which is v1 y squared equals to v1 y squared minus 2gy, that one seems to work just fine as well again. So v3y is going to be equal to squared, rather. It's going to be equal to v1y squared minus 2g, but y here is 0 because you are back at, this is right before the impact. Imagine these vectors here really belong to the center of gravity of the object, so I can redraw v3 here. This is what we're talking about. That's really where v3 is, right there. So here, y again is 0 because the origin here is 0. This is the origin line. I'll go ahead and delete this extra piece here. So the origin is chosen right here, and therefore that's 0. So 2g times 0. Guess what happened? We're getting, this is 0, so v3y magnitude was that, versus plus or minus. I mean, you got to enforce the sign here, but v3y magnitude is the same as v1y magnitude, which is the same as v1 sine theta. Now v3 is going to equal to v1 as well, and the reason for that is because both components are equal to each other. The x component is equal to each other, right? v1x equals to v3x, v1 cosine theta, and the y components are equal to each other. You can also plug it in. It doesn't hurt. You could plug it in. So you get that v3 equals to v3x, which is v1 cosine theta, squared plus v1 sine theta squared. And when we do that, we can factor v1 squared out, and we get that this is v1 squared times cosine squared theta plus sine squared theta. And for those of you that remember your trig identities, you might recognize this identity. This is a famous one. We're only concerned with those famous ones. This is actually equal to 1. We can show why that's equal to 1 in another video, but this is essentially equal to 1, and this is equal to v1. So if you plug it in, you arrive at the same exact result. All right, we still got maybe a part or two to solve. So the next part 3, says, what is the range? So these are the main questions that they can ask us. Are we looking at 4? Yeah, this is number 4. So this is saying, what is the range? Now, the range, by definition, is the maximum displacement along the x-axis, right? This is the range right here. The distance from here to where it lands along the x-axis. Now, to get the range, what we need is actually the flight time. If we have the total flight time, life becomes a lot easier. So I'm going to give a space to range, and we're going to find that in a second. But we're going to go to the last piece and look at t total, t flight. That's the amount of time that the ball is in the air. So we're looking at how long does it take to go from point 1 to point 3. Now, there is some symmetry going on in this problem that we can take advantage of. For example, if we find what is T2, how long does it take the projectile to reach that maximum height, we can double that. That's a very logical thing to do. And that will work. But You see, with that approach, what if the elevation, what if this was a cliff and while the ball started from here but landed below that origin? We want to be able to deal with that situation too. So I'm going to take a slightly different approach. Instead of doubling that time, I'm going to be looking at this equation right here, equation number 2, which is giving us the elevation. And here the unknown, of course, is time. Now I can, in this case, I can set that equal to 0 and solve for that time. But if it is below the origin in some problem, I can set that to a negative number. Say this is landing below the origin, and again solve it for time. So it will always be solving that quadratic equation. And worst case scenario, you have a C term that's non-zero, and you can use quadratic equation to solve it. So we're going to use equation number 2. Equation number 2 for the flight time is going to be y equals negative 1/2 gt squared. And then think about the flight time plus v1y t, right? And if I set that equal to 0, I can factor out the t, so I get negative 1/2 gt plus v1y equals 0. And then we can get two solutions from this. When t equals 0, this is where the projectile starts from. It's correct, but it's not where what we're interested in. That's not the t we're interested in. And the other case is when negative 1/2 gt plus v1y equals 0. And that when that happens, we solve this for t. T is going to equal to, we can move things around a little bit here. Let's actually do that. So we can add negative v1y to both sides. Treat them like just numbers, how you would treat numbers. So we get negative v1y on this side divided by negative 1/2 g. The negative signs cancel. 2 comes to the top, becomes 2v1y, which is v1 sine theta over g. Let me rewrite that a little bit better, clearly. All right, so that's going to be 2 v1 sine theta over g. Again, we can run a quick dimensional analysis on it to make sure this new expression makes sense in terms of the dimensions. So this is going to be v to 2 and sine theta, no dimension, but you got meters per second for velocity, and you got meters per second square for acceleration. Meters cancel, one of the seconds in the top cancels with one of the seconds in the bottom, and you get seconds as the result of that. So dimensionally, that makes sense. Now, if I use this, the flight time, I can actually answer the previous part much more easily about the range, because I know that the range is going to be x equal, so this is actually the range. Let's just call it the range r. So I'm going to call it r. I'm going to show you what equation I'm using. So I'm using equation number 5, this one right here, where we're saying x equals to v1x, which v1x is v1 cosine theta times t. If I plug in the flight time, that's going to give me the range. That's going to give me the maximal displacement. So we can go ahead and do that. We can say this is equal to v1 cosine theta, that's your v1x, times t flight. And t flight, of course, we just solve for it. That one is v1, 2v1 sine theta over g. So let's put the two together. That's cosine theta times 2v1 sine theta over g. And this is equal to the v1s multiply v1 squared sine theta cosine theta over g. Now we can do a couple of things here. This is the expression, but we can simplify it a little bit. So one of the things is the dimensional analysis. Let's do that very quickly. V1 squared is going to be meters squared per second squared, that's for velocity, divided by meters per second squared, that's for acceleration. Second squares cancels, one of the meters cancels, we end up with meters. Great, that's range. Range needs to be meters. Another thing is we could call 2 sine theta cosine theta using one of our trig identities called the double angle formula, sine of 2 theta. All right. So that's another thing we could do. But that's not a mandatory thing. Like, we got the expression in there. So that basically takes care of it. And these are the main questions they can ask us. They can ask us about that maximum height usually. We're going to revisit this problem from an energy perspective and conservation of energy perspective later on and derive some of the similar results from using that calculation. But this is using kinematics right now. So they can talk about what is H max. We can talk about what is the velocity at the top. We can talk about what is the velocity anywhere in the path, really. Remember, the equations we have can give us the velocity anywhere in the path. The x component of the velocity, equation 4, that's constant throughout the path. And the y velocity is going to be equation number 1. And in fact, we can also use equation number 3 to find and track that velocity along the y-axis. All right, thank you very much for your attention. See you in the next lesson.